Welcome back. We're ready to start the day 4 of the workshop, and we'll kick off with Ivan Limonchenko, who will tell us about moment-angle manifolds over Bier spheres. Please.
Thank you very much for the introduction, and thanks a lot to the organizers for giving me a chance to speak here at this wonderful workshop where I see so many friends and colleagues. Unfortunately, this time I couldn't visit Toronto personally, but hope to see all of you soon personally in the near future. So this talk is going to be based on two projects. First is ongoing research project with Professor Rade Živaljević from Mathematical Institute here in Belgrade, Serbia. And another one is a recent research project with my former student at HSE University in Moscow, Russia, Matvey Sergeyev. Now I'm going to switch to my slides. So let me first fix some notations and make some remarks about simplicial complexes. Well, of course, simplicial complexes have already been discussed here at this workshop several times, so there is no need actually to give a formal definition once again, but I just wanted to fix again some notation and make it clear what is important in the theory of Bier spheres, because Bier spheres are, of course, simplicial spheres, so we must review something about the simplicial complexes. Okay, so I will consider simplicial complexes with ghost vertices. So it means that I fix small m, which stands for the number of potential vertices, actual vertices, and ghost vertices together. It's a set of integers from 1 to m. As usual, we order vertices and ghost vertices. And, well, faces and simplices are actual faces and simplices, the elements of K, but also I can have minimal non-faces. This means a non-element in K, which is minimal in the sense that all its proper subsets are faces in K. So speaking in other words, this full subcomplex corresponding to a minimal non-face I is just a boundary of a simplex. So geometrically, it's a boundary of a simplex spanned on the vertex set capital I. This is a minimal non-face of K, and a maximal face of K is, as usual, maximal with respect to inclusion, maximal subset, maximal element with respect to inclusion. Okay, so we now reviewed what's a vertex, what's a ghost vertex, and the set of maximal simplexes I denote by m of k, and the set of minimal non-simplexes I denote mf of k. That's just my notation, and it will work in the subsequent parts of my talk. Okay, and another review, also a very important notion from combinatorics, which has already been mentioned here several times, I think, is a notion of a flag complex. So basically, you can define it in several equivalent ways, but let me fix it that a flag simplicial complex is a clique complex of a simple graph. So first of all, any simple graph is a one-dimensional simplicial complex, and vice versa, one-dimensional simplicial complex are nothing else but simple graphs. And that's a link between our theory and graph theory, of course. It was already mentioned and used several times, I think, here. And then in graphs, you may have cliques. So that's basically induced or full subcomplex, which is which can be filled in by a simplex. So vertices are pairwise joined by edges. Then you just fill in the corresponding simplex, span a simplex, and it becomes an element of this flag simplicial complex. So flag simplicial complexes are those in which minimal non-faces have no more than two vertices, because as I mentioned previously, ghost vertices are okay in this talk. And equivalently, any subset of vertices which are pairwise joined by edges spans the simplex of face. And of course, I have to say something about polytopes in this talk. So basically, a flag polytope is such a convex simple polytope that its nerve complex That's the notion also used several times in toric topology stuff. It's a boundary of the dual simplicial polytope, whose faces are simplices, is a Flach simplicial complex. So using Flach complexes, we can define Flach polytopes. And a particularly important class of Flach topes or Flach polytopes here in this talk will be this class of two truncated cubes. This was introduced in 2011 by Buchstaber and Volodin in their studying of nestahedra, and I will mention nestahedra also in this talk because of Bier spheres. And those two truncated cubes can be obtained from n-dimensional cubes by truncating, cutting off faces of codimension 2 starting from the cube and then cutting them one by one by hyperplanes in general position. So this is a family of Flach polytopes, Flach topes in n dimensions. Well, that were, as I said, some notations and remarks. And now we're ready to give this main definition. I'm going to define a Bier sphere of an arbitrary abstract simplicial complex on M. To do this, I need to recall briefly what is a combinatorial Alexander duality. So to produce a Bier sphere, one needs not only a complex K itself, but also its Alexander dual, well, K dual. Here is the formal definition. So basically, the simplices in Alexander dual are complements to non-simplices in K. In particular, since M of K and MF of K, these two sets, both uniquely determine the simplicial complex K, you can give this definition in terms of just maximal simplices and minimal non-faces. So maximal simplices of Alexander dual are just complements to minimal non-faces of K. And I have to denote M and M prime to distinguish between the vertices of K and vertices of Alexander dual, because Bier sphere is actually defined on two M vertices, on M and M prime vertices. Namely, it's the so-called deleted join of K and K dual. So deleted join, of course, can be defined for two arbitrary simplicial complexes on the same vertex set, on the vertex sets having the same cardinality. But here you take K and K dual. What you obtain is some simplicial complex, and later in this talk we will recall its main combinatorial properties because we will need them. So for now, it's just an abstract simplicial complex on two M vertices. And of course, when we consider the first examples, we already see that this Bier sphere can have ghost vertices. For example, the first example is you can take boundary of a simplex, and so its dual will be an empty simplicial complex, a complex in which each vertex is a ghost vertex. And if you consider the deleted join, then of course it will remain to be the boundary of a simplex on M vertices. And so it's an M minus 2-dimensional sphere sitting on M prime and having M as its ghost vertices. Well, actually, this can be generalized, and we will see that it's always M minus 2-dimensional sphere, and the number of geometric actual vertices is always varying between M and 2M. Like here, it's M, and of course it can be 2M, and basically everything between them. Another general remark is that, of course, Alexander duality, dual of the dual is the initial complex K, and immediately from this you see that Bier K and Bier K dual are simplicially isomorphic. There is a natural isomorphism. You can identify those two simplicial complexes, those two spheres. And so when you try to classify them, and that's what we're going to do right now for low dimensions, you will have possibility to choose either you consider K or K dual, but you do not need to consider both of them because they give you the same sphere. So continuing with our first examples, here is the complete classification of Bier spheres in dimension 1. Well, since it's actually always m minus 2-dimensional sphere, then we should take m equals 3. And if we take m equals 3, the only possibilities up to duality, up to Alexander duality, will be listed here. So the resulting Bier sphere is either a triangle or, well, boundary of a square or boundary of a pentagon or boundary of a hexagon. So you see this classification, and from this classification, people who know and love nestahedra like myself, they immediately realize that those guys are actually nothing else but two-dimensional nestahedra polygons. Triangle, square, pentagon, and hexagon, that's it. And it also has a deep meaning, actually. We will see it. But here is the classification in the second dimension. Together with my former student, Matvey Sergeyev, we did all possible combinatorial types of two-dimensional Bier spheres. So we know that in dimension 2, the Simplicial Steinitz problem has a positive solution. I mean that any two-dimensional simplicial sphere is polytopal. It's a boundary of a certain simplicial convex polytope. And you see those 13 polytopes right here in this table. So the left thing on the left-hand side, you see the sphere, the Bier sphere, and on the right-hand side, you see the corresponding simplicial three-dimensional polytope. And you see these three-dimensional polytopes, some of them are flagged, but mostly they are non-flagged, because those non-flag ones were obtained by cutting a vertex, so they're non-flag. But those that are flagged, they are actually two truncated cubes. They're actually two truncated cubes, and moreover, they are flag nestahedra. Actually, Buchstaber and Volodin proved that each flag nestahedra is a two truncated cube. That means it has such a realization. And here, Matvey and I just did this to truncated cube realization so that you can see, for example, this prisms and a three-dimensional cube with two adjacent edges cut, like this P4, which we will need in subsequent slides, the P4, such a two truncated cubes. Okay, and now these first examples motivate some open questions and some further discussion. So let me briefly mention two open problems here in this area. First one is just something like Simplicial Steinitz problem for Bier spheres. This unfortunately still remains open, so nobody was able to find the simplicial complex K such that its Bier sphere is non-polytopal. So it cannot be isomorphic to a boundary of a simplicial polytope. So people, my colleagues actually are now working on this. And so far, no examples are known. But you see in this slide that there is some nice result about enumeration of different types of Bier spheres and enumeration of polytopes. And actually, this enumeration shows that non-polytopal Bier spheres actually exist. And moreover, the majority of Bier spheres are non-polytopal. So this is, again, a typical mathematical situation where, like with transcendental numbers, for example, that the majority of numbers are transcendental, I mean real numbers, but it was an issue, a problem, how to construct or find a concrete example. And here is with Bier spheres, we still have the same kind of challenge. We are trying to construct to prove that a certain Bier sphere is non-polytopal. And the second problem related to that classification we have is that to find necessary and sufficient conditions on combinatorics of K such that its Bier sphere can be realized as a nested set complex. And by nested set complex, I mean the nerve complex of a certain nestahedron. So this is just motivated by the previous examples because you saw that actually all one-dimensional Bier spheres are nestahedra, and all but one two-dimensional Bier spheres are also nestahedra. So this is just a natural question to ask. Well, to proceed with general combinatorial and geometric properties of Bier spheres that we need, we need to review something about polyhedra and geometric realizations of simplicial complexes. Again, this is just to fix notations because I'm sure that all of you know that if you have an arbitrary simplicial complex and you can have the corresponding geometric simplicial complex of polyhedron in certain Euclidean space Rn, whereas the dimension can be probably bigger than the dimension of the abstract simplicial complex, but you can basically realize any abstract simplicial complex. And actually, by Nöbeling-Pontryagin famous theorem, it's of course much more general than that, but any simplicial complex of dimension n can be realized geometrically in R2n plus 1. So you of course have geometric realization. And basically, to define geometric realization, you need to define a bijection between the vertex set of your abstract simplicial complex and the vertex set of the simplices in P in the polyhedron, such that this map sends simplices of K to vertex sets of faces of simplices of P. And that gives you geometric realizations. So, well, after this standard thing, I also need to review what a map between two polyhedra is or can be. So good maps between polyhedra here in this talk are simplicial maps and PL maps. Well, simplicial map, like in the case of abstract simplicial complexes, a simplicial map is just a map from vertex set to vertex set such that simplices go to simplices. And here, of course, just literally the same. The vertices go to vertices geometrically, and geometric faces spanned by those vertices go to geometric span faces spanned by those vertices linearly on each face. And simplicial isomorphism, as we know from category theory, is just a simplicial map such that the inverse simplicial map exists in this category. PL map is a simplicial map on a certain subdivision of P1 to a certain subdivision, a simplicial map from a certain subdivision of P1 to a certain subdivision of P2. So you might have no simplicial map between P1 and P2, but you need to subdivide the domain and codomain, and then you will have a simplicial map between them. So this is a more general situation, and it's called PL. PL map, and PL homeo is, of course, PL, and the inverse is also PL. Well, we are almost ready to define the classes of spheres we are going to discuss in this talk. But before that, I just need to recall the notion of a link in a simplicial complex. Also, of course, used many times in Toric topology and discussed here in this great workshop. A link of a simplex in K is just all simplices such that they do not intersect this one, but in the union, you obtain a simplex in K. So up from now on, I would like to assume that an empty set, the empty set, is an element of K. And so immediately from this definition, you have that link of this empty set is just the whole simplicial complex K. This will help me to define homology spheres in the next slide. So here are 5 classes of combinatorial spheres that are classical in combinatorial commutative algebra, and also that are very important in Toric topology. And they are important for us now because we will say a few words about Bier spheres and the class they belong to. To do this, we need to review polytopal spheres. I already mentioned them in the beginning of this lecture. It's actually a simplicial complex isomorphic to the boundary of a simplicial and polytope. Well, from now on, I will sometimes use interchangeably simplicial complex and its geometric realization. Please forgive me. It's just a jargon, so please. A star-shaped sphere, that's maybe the most important because of our results today. So star-shaped sphere can be defined in two equivalent ways. The first way is you define it using fan theory. Well, I'm not going, of course, to review here in this great audience what a fan is, polyhedral fan, because it's one of the key notions from Toric geometry. And I'm going to say that if you have a fan, then you associate with it a simplicial complex, because from definition of fan, cones in a fan should, well, intersections of cone is another cone, and all subcones are elements of a fan. So generally it reproduces definition of a simplicial complex. So with each fan, we uniquely associate a simplicial complex. And this corresponding simplicial complex should correspond to a complete simplicial fan. This is definition one, and the equivalent definition of that geometric realization of a star-shaped sphere is such that it lies in Rn, and there is a point in the space Rn such that, considering each ray emanating from that point, the ray intersects your realization in exactly one point. Well, this is classical from convex geometry, convex analysis. You know what a star-shaped region is from geometry, and this convex geometry is applied here. So convex region is just bounded by this star-shaped sphere, star-shaped region. And then PL sphere is a simplicial complex PL homomorphic to the boundary of a simplex of the corresponding dimension. Simplicial sphere or triangulated sphere, the most basic type of spheres we consider in toric topology, is just any simplicial complex of polyhedron homeomorphic to Sn-1. And finally, rational homology sphere is such a simplicial complex that for each simplex, the link will be a homology sphere of the corresponding dimension. So here I just mentioned the formula for homology, but it basically means that it's a homology sphere of dimension n-1 minus number of elements in sigma. As I mentioned, the empty simplex is a simplex in K. So if you consider sigma being an empty set, you will obtain that K itself is a homology sphere. So in literature, homology spheres can have different definition, but that's the definition which I'm using here. Okay, and now we are ready to say more about the structure of Bier spheres. Well, this is a classical result dating back to the original note by Thomas Bier, 1992, who introduced Bier spheres and this construction we already discussed. And he stated there that H Bier sphere is a -2 dimensional PL sphere, and the number of vertices, as we mentioned, is varying between M and 2M always. Well, and actually, he produced some proof. You can see it in the monograph by Matuszek, for example. But then de Longueville, who is, I think, known to us, to specialists in toric topology, he came up with a very nice construction, a very clear geometrical description of what is happening with this corresponding PL homeomorphism. Then actually, the second part of the statement is a proof of the first one. You can consider it as such because he just says that if one replaces a simplex in Bier sphere, a simplex is of type sigma plus tau, sigma is in K and tau is in K dual. If you replace this guy with the corresponding, with the join of corresponding barycentric subdivisions of those simplices, you will obtain nothing else but the barycentric subdivision of the boundary of the whole simplex. And that basically means that you will have a PL sphere, that each Bier sphere is a PL sphere. Here is the PL homeomorphism. Well, we know that barycentric subdivision of the boundary of a simplex is the nerve complex of a permutahedron, an extremely important example of an estahedron, flag nestahedron actually. And so when we talk about combinatorics of Bier spheres, naturally arises combinatorics of permutahedra, and dually It's a so-called braid arrangement fan that is nothing else but a normal fan of a polyhedra. We will see it. Now, first main result of this talk is concerned with phase vectors of Bier spheres. To do this, I just briefly recall what a phase vector of a simplicial complex is. Well, here I just gave it to simplicial polytope, but of course simplicial complex is just generalization in a certain sense, so you can use the same formulas to define f, g, and h vectors for any simplicial complex. These are some familiar formulas also used in toric topology. And the gamma vector is can be defined only if h vector is symmetric, but h vector is really symmetric not only for polytopal spheres, but as we know from enumerative combinatorics, for any simplicial or even homology sphere by Denso-Merville equations, and these equations hold for any homology sphere. So we can define gamma vector also. These are formal definitions, and our results are concerned with gamma vectors, because I would like to consider today the next four conjectures in enumerative combinatorics of Flach homology spheres. Well, we again we can pay attention to pay tribute to great results of Karima Di Prasite, who in 2018 announced that a solution of the G theorem for all homology spheres, and the Denso-Merville equations, as we know, is a part of this necessity part in the necessity part of G theorem, so it holds for any homology sphere, as I mentioned. So gamma vectors are defined, and here are the conjectures about them. If K is a Flach homology sphere, then its phase vector is component-wise non-negative. This is a famous Gall conjecture. It also implies, for example, Cherny-Davis conjecture, which has a long history and is related with different areas in mathematics. This conjecture says that gamma vector of a Flach homology sphere is component-wise greater or equal than gamma vector of a cube, actually. And the more general Neveu-Petersen conjecture, stated in 2010, is that for any Flach homology sphere, actually gamma of k is not only component-wise non-negative, but also it's a phase vector of a Flach simplicial complex. So it should be non-negative. Okay, and now there were some results trying to prove or disprove this conjecture. Neveu and Petersen showed that this is true for all simplicial complexes, Flach homology spheres with gamma 1 not greater than 3. And more recently, Eisbeth and Volodin proved that this conjecture is true for any two truncated cube. That's related to our results. And finally, I would also like to mention these two conjectures from the paper by Chudnovsky and Neveu, which actually this link conjecture, they showed it is more general than Gall's conjecture and implies Gall's conjecture, more strong. So for any Flach homology sphere, gamma of k is component-wise greater or equal to gamma of link of a vertex. Well, you know that for Flach complexes, link is a full subcomplex, and it's also Flach, and also it's a homology sphere. And they generalized it in the same paper for equators and Flach homology spheres. An equator is a full subcomplex that is a Flach homology sphere of codimension 1. This is called equator, like an equator on the globe. And the following conjecture just directly generalizes this, so you can replace link of a vertex by any equator in the Flach homology sphere, and you have this coefficient-wise inequality. Well, Chudnovsky and Neveu proved that this holds for any three-dimensional two-truncated cube. That's what we knew for now, and our result with Professor Zhibalevich is that both Neveu-Petersen and equator conjectures are true for Flach Bier spheres. Well, this is proved, and the key step in this proof is the classification of all Flag-Bier spheres. It's actually, it actually turns out that all Flag-Bier spheres are polytopal spheres, and there are not so many of them. And actually, they can be only cubes and products of cube and a pentagon, products of cube and a hexagon, and products of cube and P4. That P4 stands for this two truncated cube from the classification of two-dimensional Bier spheres. It is obtained from three-dimensional cube by performing two adjacent edge cuts. So this is all, and then we directly checked that these conjectures, and actually the four conjectures I mentioned, because they are the most strong ones, the Nevo-Peterson and Equator, they imply other two, they hold for Flag-Bier spheres. Here's the complete classification. Well, now in the final part of my talk, I'm going to turn to polyhedral products finally, so this is the workshop about polyhedral products finally, and I need to introduce our results about polyhedral products now. Well, first applications of Bier spheres are more or less clear, because K is always a full subcomplex in Bier K, and that's true for any simplicial complex on any vertex set, we immediately obtain that moment angle complex over Bier sphere might have an arbitrary torsion in integral homology. This is probably another way to show that moment angle manifolds can have arbitrary torsion and integer homology. Another one was introduced by Bossier and Meersman, using truncations of a boundary of a simplex. And another observation directly from definition is that cohomology algebra of the moment angle complex over Bier sphere can contain any higher order decomposable or indecomposable non-trivial massy product that you can realize using K and moment angle complex of K. Again, by the description of cohomology algebra that we all know and love, and it was already mentioned several times in this workshop. And I want to mention that actually, probably this was the chronologically first application of Bier spheres in the context of toric topology, and it belongs to Alex and Graham in 2007, a great paper about monomial ideals and massy products, where they used it to show that there is a moment angle manifold having an indecomposable non-trivial triple massy product in cohomology. Now we make a further step from these observations, and we will be interested in two particularly important types of polyhedral product construction: real moment angle complex R of K and complex moment angle complex ZK. And well, as a motivation for this part of the talk, I would like to mention this very nice structure results actually, belonging to Tsai Li and to Panov-Ustinovsky and independently to Jerome Tambour. If K is a simplicial complex on M, and its dimension is n-1, this is the usual convention in toric topology, n is greater or equal than 3, then Tsai Li showed that R of K has a structure of a topological and manifold if and only if K is a simply connected homology sphere. He calls it generalized homology sphere in his paper, but according to our definition of a homology sphere, it's actually what we have as a homology sphere, not, well, he calls generalized homology sphere. And the same paper, he shows that ZK has a structure of a topological n plus m dimensional manifold if and only if K is just a homology sphere. You do not need the assumption of simply connectedness here. And the second result belongs, as I mentioned, to Panov-Ustinovsky and Tambour. They were interested in smooth structure on these polyhedral products. And actually, if K is a star-shaped sphere, equivalently the corresponding fan is complete and simplicial, then both R of k and Z of k are homeomorphic to smooth manifolds, and actually they have equivariant smooth structure. Well, motivated by this, we considered this result by our Serbian colleagues, Jeftić, Timotijević, and Živaljević, who were interested in Bier spheres from the viewpoint of convex geometry and combinatorics, and they proved in 2019 that any Bier sphere, Bier of K, has a realization as a star-shaped sphere. Their realization is a certain sense canonical one, and it lives in the hyperplane H0 with a normal vector, just sum of all standard basis vectors living in Rm. So this is, of course, m minus 2-dimensional sphere. It bounds an m minus 1-dimensional star-shaped region in this hyperplane H0. Well, from this, since it's a star-shaped sphere, and the previous result shows that the corresponding moment angle complexes, both real and complex ones, acquire equivariant smooth structures. So from now on, we talk about moment angle manifolds, smooth moment angle manifolds over Bier spheres, as the title of my talk suggests. This is actually the foundation for the further study of the corresponding smooth manifolds related to Bier spheres. And we decided to put some toric topology on this, and together with Matvei, we observed that for any Bier sphere on M, where M starts from 2, both complex and real Buchstaber numbers that are just the highest possible rank of a subtorus in Tm acting freely on the corresponding complex or real moment angle complex. So this rank is always m plus 1. So they coincide, and for each m you have m plus 1. And the corresponding characteristic map that corresponds to this Buchstaber number simply sends I and the corresponding I prime from the Alexander dual complex to EI. And we can send m and m prime to U, where U stands for the sum of standard basis vectors. E1 plus E2 plus etc. plus EM minus 1. Here you have Rm minus 1, so you have m minus 1 standard basis vectors. Their sum is U. And here are the explicit formulas for this characteristic map. But that was only first step, because next we were interested in trying to use these observations and construct a complete regular fan for any Bier sphere. And we succeeded actually, and that's our, as I mentioned, our ongoing research project with Professor Živaljević. For any simplicial complex, of course, I should say different from the whole simplex on the M vertices, because Bier spheres are not defined for the complete simplex. Bier sphere is isomorphic to the underlying complex of a complete regular fan in Rm minus 1. And here is the description of the cones of this regular not complete fan. The generators, the extreme rays, are generated by plus or minus basis vectors, plus the vector Em is minus U. So whenever you have P of Q equals M, then it's plus or minus U. And so this is, if this is a fan, then obviously it's regular. And to prove that it's a complete fan, we actually use the completeness of the fan from Jeftić, Timotijević, and Živaljević. We kind of perform certain operation on it, and we obtain this one. So it remains to be a complete fan, and it's regular, and we are done. Well, what shows this result, it actually says that starting with an arbitrary simplicial complex K on M, we get two nice canonical, in a certain sense, smooth manifolds. The first one is the canonical smooth moment angle manifold. I just mentioned here the complex moment angle manifold, but of course, you can add the corresponding real one, R of Bier K. It will have the corresponding dimension. Here's the complex one, of course, has dimension 3m minus 1. And at the same time, you now have a canonical smooth toric manifold, and its dimension is 2 times m minus 1. So starting with arbitrary simplicial complex k on m, you end up with a certain toric manifold. And so in this project, we're interested in some differential geometric and topological properties of these toric manifolds. And all comments and suggestions for further development of this and applications would be greatly appreciated. Well, finally, in this last slides, I just wanted to give you an example of our construction, what this complete regular fan looks like. Here is m equals 3, and I take k with maximal simplices 1 and 2, 3. If I do this, then it can be easily checked from the definition that the maximal simplices of the corresponding Bier k are this just 5 edges, and actually it's a pentagon. It was already mentioned in one of the slides in the first half of my talk. That was classification of one-dimensional Bier spheres. It's a boundary of a pentagon. And you see very familiar complete regular fan corresponding to this pentagon. It's here. Well, this is an example. And finally, regarding some immediate applications of these constructions, well, we have more, but for now, I just wanted to mention briefly the two corollaries. The first corollary immediately from the construction of toric manifold is that then-Somerville equations hold for all Bier spheres. Well, of course, this is not a new result, since then-Somerville equations are known to hold for any simplicial sphere. That's first of all. And secondly, for Bier spheres, they were proved by Björner et al. In 2005 in this purely combinatorial way, in combinatorial enumerative techniques. But we just have immediate consequence, topological proof of then-Somerville equations for all Bier spheres. And the first corollary and the second corollary, again, this is a known result in toric topology. Yusuke Suyama proved in 2015, it was published, that there are infinitely many toric manifolds whose orbit spaces are not even homeomorphic to any simple polytope, these manifolds with corners. So basically, you have a toric manifold which is not a quasi-toric manifold, something like this, I think. And yes, still, we do not have a concrete example of a non-polytopal Bier sphere, as I mentioned, but we have a result that the majority of Bier spheres are non-polytopal, and combining it with our result, it means that all those give us examples, infinitely many examples of such toric manifolds. So Yusuke used non-polytopality of this famous Barnett sphere, a 3-sphere with 8 vertices. So it's actually absolutely different idea from the theory of Bier spheres, but we see that Bier spheres applied here, given a different way, a different proof of this result. Well, this is some references regarding Bier spheres. So for those of you who are interested in this from the combinatorial side, you can check these references for more properties, more combinatorial geometric properties of Bier spheres. But I think that our projects with Matvey and Rade are the first ones that put in Bier spheres in the framework of toric topology. So I hope this will be continued. And for now, let me stop here and thank you very much for your attention.